Welcome to Chapter 8 on linear momentum and collisions. We're going to cover several aspects of momentum and collisions here, but let's start with what is momentum. All right, momentum is a vector. And it's a vector because momentum is just mass times velocity, and velocity is a vector. Right? We don't have a special unit for momentum. Based on this simple definition, momentum is mass times velocity. We have kilograms meters per second are the units that make up the momentum, right? So we don't have a separate unit for it. We just call it kilograms meters per second. All right. So another part of momentum, if we look at the net force, is mass times acceleration, and then we go back and we say, oh well, acceleration is change in velocity over change in time. We can move the mass in there, and we get to, the net force is just the change of momentum over the change in time. All right, so a force applied, an external net force applied, gives us a change in momentum over time. Cool thing about this is that we then define what we call the impulse. All right, the impulse is a force applied over a certain amount of time, and that gives us the change in momentum. Right? Understanding impulse, understanding how this works has led to all kinds of safety precautions and safety advantages that we have in modern automobiles and football helmets, any number of other things as we work through how do we absorb this momentum? How do we absorb this change of momentum? And we're going to get the change of momentum. That's actually the fixed part. What we're trying to do is reduce the amount of force, and what we typically do to do that is we use bumpers and we use other things like that to spread the crash out over time so that this delta t part is longer, which makes the force part smaller. Momentum is a conserved quantity. In any isolated system, momentum is conserved. So if we look at the system of these two cars and we look at them crashing together, their total momentum is conserved, right? What does that mean? That means, and here's why total momentum is conserved. The total net force of any isolated system is zero, right? There's no external force on an isolated system. So the momentum has to stay the same, right? If this term is zero, change in momentum has to be zero. So momentum has to be the same before and after. And the way we put that is we say the total momentum before equals the total momentum after. You got to keep in mind this is a vector, and so that means the x component of the total momentum before the collision and the x component of the total momentum after the collision are equal, and the y component of the total momentum before the collision and the y component of the total momentum after the collision are equal. Now, that momentum may be distributed differently among the different objects within the isolated system, right? That's the point behind collisions. The momentum gets redistributed, but the total momentum remains the same. The way we write this, we have two cars. We got P1 plus P2, and the little prime indicates this is after some event. So P1 plus P2 equals P1 prime plus P2 prime. And remember, these are all vectors. In what we call an elastic collision, not only is momentum conserved, but kinetic energy is conserved. And that means if you sum up all the kinetic energy before the collision and you sum up all the kinetic energy after the collision, that they add up to be the same. So in an elastic collision, kinetic energy is conserved is the same before and after the collision. In inelastic collisions, that's not true. Right? In inelastic collisions, what happens, the reason they're called inelastic collisions, is some of the kinetic energy goes into doing work in some way. If these were a couple of cars, it went into smushing the cars. If these are just two blocks that have Velcro on them, right? All right, if these are just two blocks that have Velcro on them and they can't bounce off of each other and they stick together afterwards, That's going to be an inelastic collision. The kinetic energy afterwards is going to be different from the kinetic energy before. And where did that kinetic energy go? It went into forming that bond between the blocks. It went into noise. It went into a number of different places. All right. So let's review real quick. Total momentum comes from momentum, mass times velocity. All right. Force is change in momentum over time. Total momentum is conserved. Right? So the total momentum before and the total momentum after are the same. In elastic collisions, total kinetic energy before and total kinetic energy afterwards are the same. And in inelastic collisions, the kinetic energy changes from before to after. Kinetic energy is not conserved. All right, that's it for part 1 of chapter 8.